Okay, in this video we're having a look at chapter 5.3, which is families of polynomials. So we've had a look as a starting point, we had a look at linear polynomials. Okay, so they're straight lines, not much to them, still polynomials nonetheless. Once we get into powers of 2, 3, 4 and beyond, we start to get curves within the shape of the polynomial. So we like linear shapes or linear polynomials because they are straight line, easy to deal with, and to do calculations. But once we get into higher degrees, so polynomials of 2, 3, 4, they start to show other similarities between each other. And so what we do is we try to separate them into two categories, those with odd degree and those with even degree. So as a starting point, we're going to have a look at graphs of x to the power of n. So as a starting point, x to the n. Okay, and n is an element of all the natural numbers, so even degree and positive powers. And for this example, we're going to have a look at for n is odd. So just the odd numbers, so 3, 5, 7, etc. Okay, so we use n to describe these numbers, just depending on what number we want. So just considering shapes with power degree n, where n is odd, we get some similarities between them. Okay, so I've drawn what's the first odd degree power, which is obviously power of 1, and that's linear. So this is just a straight line, and we're going to compare what this looks like once we compare it to the other degrees of 3, 5. I probably won't go further than 5. So that's a starting point. So we've got a straight line goes through the points 1, 1 and minus 1, minus 1. Pretty straightforward. In the next part, I've drawn a graph of the y equals x cubed, so a cubic graph. Just follows that shape. Now, obviously very different to a straight line. That's because we've got starting to get, so we've got curves and so we've got a stationary point of inflection now. Okay, but that's the general shape of a x cubed graph. They both go into points 1, 1 and negative 1, negative 1. So there's already a similarity between them. And the last graph is y equals x to the power of 5. So in black we can see, okay, very sharp outside the region once we go past 1, but very close to the x-axis as we go in further towards 0. Okay, very similar shape to the x cubed graph, where it follows this path, and again got a stationary point of inflection through the origin, and it just follows that shape. All three graphs start to go through, or they all go through 1, 1 and minus 1, 1, minus 1, minus 1. Okay, the only difference at the moment is that x to the power of 5, as we go larger numbers across to the right or the left, we're going to get steeper numbers either up or down. So now we'll just have a look at a comparison of the graphs of, so our three graphs of y equals x x cubed, and y equals x to the 5. So what are the similarities? Well, as x gets larger, so approaches plus or minus infinity, so as we go to the right, as we go to the left, okay, we're approaching infinity. What happens to the y? Well, that also approaches infinity as well. So as we go across the right, infinity, or the y values are going to go steeply and go up towards infinity. And same with the left. So as we go across the left, our numbers are going to go down towards infinity. So there's the first similarities, and that occurs for each value of x. It just so happens that this goes at a faster rate for the x to the 5. But same thing for x to the cube, it just doesn't happen as quick. As I said before, all three graphs go through the point 1, 1 and minus 1. So goes through 1, 1, minus 1, minus 1, and 0, 0, which I didn't point out before. They all go through the origin because we haven't moved it left or right. And with the exception of the y equals x graph, the other two graphs have a stationary point of inflection, as I said, through, in this case it's going to be at the origin, so it doesn't move. So we've got x cubed and x to the 5 have a stationary point of inflection. And this is at the point 0, 0. So the larger power, the higher the power, the more narrow it is for x values greater than 1. So after 1, as I said before, we're going to get really steep for the x to the 5, and after minus 1 we're getting really steep in a negative direction for x to the 5. Now the same thing happens for x to the cube. We also get quite large and steep numbers as we go past minus 1 and positive 1. But between those 2 points we get very close or very shallow in comparison towards the x-axis. So not much to really say there for that last part, just something to note. So in summary, we can say if n is an odd positive integer, so n is odd positive integer, we can say that y equals x to the n will have a stationary point of inflection at 0, 0. And what it'll do is basically, for the higher numbers of n, it's going to follow the same similar shape as x to the cube, x to the 3, so x cubed. It's going to have the same shape. Yes, it's going to be more narrower after 1 and minus 1, but essentially it's just going to follow the same shape. So that's a little summary there. And just to finish the definition, so we've looked at, as a general equation, y equals a, x take h to the n plus k. Okay, we're going to have a stationary point of inflection at h, k, and we've looked at that. So stationary point of inflection at hk. Now, if a is greater than 0, then x is going to approach positive and negative infinity. So as x approaches positive and negative infinity, y also approaches it. But if a is less than 0, as x approaches positive and negative infinity, y is going to approach the opposite of it, so negative and positive infinity. So if x approaches 100, y is going to approach minus 100. And that's for the odd powers of graphs. So for n is less than, n is 1, 3, 5, etc. If it's in this shape, this form, we're going to have one x-intercept, and it's calculated by solving for 0, for when y equals 0, so 0 equals a x take h to the n plus k, and there's only going to be one y-intercept, and that's calculated as usual by just subbing x equals 0 into the equation. So that's a little summary of odd powers, and we'll go into an example in a moment.